Hello, everyone, and welcome to this Flexible Circuit Technologies webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenters. With us today, we have Mark Finstead. Mark is the Vice Chairman of the IPC Flexible Circuits Committee, Chairman of IPC 2223 Flexible Circuit Design Standard. He also sits on the IPC 6013, IPC-4202, IPC-4203, and IPC-4204 committees, and has over 40 years of experience designing and manufacturing flexible circuits and heaters for commercial, medical, and military avionics applications. He has authored articles in numerous trade magazines and currently co-authors the Ask the Flexpert column for PCD and F magazine. Also joining us today is Chris Clark. Chris has spent the last 35 years of his career designing and building flexible circuits, rigid flex, and flexible heaters, serving applications for almost every industry. He is CID certified and sits on the IPC-223, IPC-6013, IPC-4202, IPC-4203, and IPC-4204 committees. Clark has written articles in several trade magazines. All right, gentlemen, I'd like to welcome you all to today's event. Now I'm going to pass things over to our flexible circuit moderator today, and that is Ray Cottrell. Ray, the floor is yours.
Thanks, Katie, and good morning, good afternoon, and good evening to all. So I just want to make sure we're on the About Us slide. Can you confirm that, please?
Yes.
We're on the About Us slide, Ray. Go right ahead.
All right, thank you. So my name is Ray Cottrell. I'm the Executive Vice President of Business Development for Flexible Circuit Technologies, or FCT for short. And on behalf of our entire team, really wanted to thank the global community joining us today for this overview of catheter designs. And before Mark and Chris share some of their nearly 80 years of combined flex design expertise, experience that you can tap into for your support when you optimize your catheter designs for functionality and cost, we just wanted to spend a few minutes on our advanced medical manufacturing capabilities, as well as our world-class flex circuit facilities. So this slide really highlights kind of where we're at today. We are celebrating our 25th year of serving the medical community. It is our birthday in May. And as this highlights, we focus on and lead with our industry-leading flex design team, but we support that with truly advanced in-house manufacturing of flex circuits, rigid flex, flex heaters, membrane switches, and medical plastic moldings as your needs dictate once you get through with your catheter designs. We have lots of other opportunities to bring value add to the medical community through a lot of different product offerings and services. As we go to market, we are branded under FCT, or Flexible Circuit Technologies. And underneath that umbrella holding company, we have the Bear Circuit facility, which is 500,000 square feet of truly an amazing state-of-the-art Bear Circuit facilities, and that is under FCT, or Flexible Circuit Technologies. In addition to that, we have a medical-focused EMS group called IntFlex, or Integrator of Flexible Solutions. This is state-of-the-art, newly invested in over the last 2 years, 900,000 square feet of opportunity to engage with us on additional value add when it comes to printed circuit board assembly up through and to box build. And that is a ISO 1345 and medical approved facility as well. In addition to that, we also offer SteriMed, which is our medical plastics group that has EO sterilization and of course is 13485 as well. So when you look at some of our capabilities and facilities, over the last 4 years, we've invested around $80 million in new equipment to support the medical community in advanced circuitry, as well as advanced manufacturing for medical products. Highlighting Zhuhai, which is the Bear Circuit facility under FCT again. That's in the upper right-hand corner there with the arrow. And underneath that is our newest EMS campus, which is absolutely amazing as far as the technology and the high-speed equipment that we have there for quality medical manufacturing. In addition to this tariff situation that has popped up over the last handful of months or quarters, we have a roadmap and currently are looking at expanding our operations into Thailand as well to offer additional flexibility to our medical partners. So when you are looking at engaging with any company and getting through your catheter design, the ability and capability to engage with us in a variety of ways is really up to you to kind of push and lead us in the direction that offers you and your supply chain and sourcing team the best path to optimizing and bringing your products to market. Within the global landscape, over the last 18 to 24 months, we have expanded our reach with direct and indirect personnel kind of sprinkled around the globe. So it offers us the ability to engage with you, hopefully within your time zone and geography, as we look at either bringing new designs to the marketplace or supporting you on cost downs, supply chain strategies, or EMS contract manufacturing. With a variety of certifications, of course, medical being 1345, we've also invested in and have certifications and registrations for EMS, environmental management systems, other certifications for supporting our workers, making sure that we're controlling and managing IP properly, and advancing human rights within the scope of many different accreditations and certifications within the family. So in summary, and at a high level, I will say we have a wealth of knowledge within the design team, truly a world-class design team supported with advanced and industry-leading facilities in manufacturing. We can engage with you to bring your products to market from prototypes to NPI into high-volume production, whether it's for your catheter circuits that we're speaking to you about today, or additional value add when it comes to sub-assemblies or full box builds. We have the talent, the medical processes and facility to support your innovation, your innovative products, and bring them to market quickly with quality medical manufacturing. I'll highlight, we did have a tier one OEM. I think there's some participants on the phone from that company visit us over the last 3 months. And a comment that came out of it after they visited both our facilities was, "You make our heart sing." So I'll take that as a good thing, just showcasing that we are able to offer a tier one OEM with a lot of additional incremental value on the products they were bringing to market. So as I hand it over to Mark Finstead, our Director of Engineering, and in summarizing it, we have a tremendous team around the globe through program managers, customer service folks, and just within the CAD and application engineering team, we have over 300 years of combined expertise. And as I highlighted earlier, just between Mark and Chris, we have roughly 80 years doing flex design. So on that, I appreciate, again, you joining us today, and I'll turn it over to Mr. Mark Finstead.
Thanks, Ray. I'd like to talk briefly about the reasons that would drive a designer to use a flexible circuit across virtually any application. But as I discuss these features, it should become clear very quickly why flexible circuitry is such an attractive interconnect technology for use in catheters. It's first important to understand that flex circuits are not typically used to replace rigid PCBs. While they certainly could be used for that application, that's usually what is not the primary driver. In most applications, flex circuits are used to replace wire bundles or wire harnesses. So if you picture a bundle of wires that are zip tied together, if you were to cut that wire bundle and view the end cut, you'd see that much of the cross-sectional area is consumed by wires insulation and also the space between the wire insulation, because round wires don't stack well. Because the dielectric materials in flex circuits are so thin, and because the cross-sectional shape of our traces is roughly flat or rectangular, we can pack our conductors into a much tighter space. with only a few thousandths of an inch space between below and adjacent to other conductors. The end result is a much higher kind of connection density, which takes up a fraction of the space of a wire harness. The implantable medical market was really the first to embrace flex circuits. And they did it mainly because when they were doing the first cardiac implants, the devices were really big. It was like getting a color TV installed in your chest. So as the engineers worked to try and shrink those devices down, they looked at what was taking up the majority of the volume, and they found that much of it was coming from wires and from the batteries. And so they went off and looked at both of those options to see what they could do to shrink it, and they found that by going with flex circuits, they could get rid of a lot of those wires, and that allowed them to get down to the current sizing, which is about the size of a pack of Tic Tacs. So if you look at this slide here, you can see that many of the top uses are cardiac and medical, and that's still a very large portion of the medical or the flex circuit market. But really, they're used in pretty much every application that's electronic. Everything from aircraft, automotive, computers. You see it in hearing aids, any place where space is an issue. I'll go through these individual advantages kind of one at a time, but there's a lot of things that flex circuits bring to the market that you can't get in a wire harness. One of them is weight, and that's really, really big when it comes to things like avionics or applications for munitions. The amount of weight that you get rid of is, I would say that the 40 to 50% is a conservative estimate. And so for applications where you're seeing high shock and vibration or high G-force, flex circuits will survive really, really well, where if you had a bundle of wires and connectors, they'd fall apart really pretty quickly. This is also a big benefit. When we do our flex circuit designs, all the conductors can be perfectly matched. So in your differential pairs, you can have exact match lengths for all of your pairs. There's no way you can match that with a wire harness. By the time you've stripped and soldered your wires, things get out of whack. And with catheters in particular, because of the length, the longer those wires would be, the more critical those lengths are. And so for high-speed applications, flex circuit can give you performance that you just can't get with a wire harness or a wire bundle. If you look at reliability, and this is pretty much in any system, whether it's your house or an electronic assembly, the failures rarely occur in the middle of a run. It's usually where you have solder joints or wired connections. And flex circuits can eliminate a lot of those because all of your conductors are on a single substrate, and so you don't have all of the individual connections that are prone to failure. I'm going to be going over this a little bit more on the cost drivers later on. This slide just shows the different specifications that you want to use when you are designing your flexible circuit. I want to point out in particular the flex circuit materials designations, the IPC 4200 series. It's important when you're designing your flex circuits, whether it's for catheters or any other flex circuit, that you specify your materials based on the IPC specifications and not on particular brands. From a cost standpoint, the reason for that is that every manufacturer is going to stock a couple of brands of IPC certified materials. And because of the volume that they use, they're going to get preferential pricing on it. If you go to your manufacturer and you specify materials that are not part of their bulk buys, they're going to be paying a premium on those. And you also will have lead time and sometimes just availability issues. So it's important to specify per the IPC specifications, and any material that's specified for the IPC specifications will be drop-in replacement. So you're not really losing anything as far as value on those materials. And on that, I'm going to turn it over to Chris on what is a catheter circuit.
All right. Hello, everyone. So what is a catheter circuit? So historically, catheters have been used to treat, ailments and procedures from cardiovascular, GI, neurovascular, urological, and ophthalmic conditions. I did a little Googling this morning, and the first heart-focused catheters were used on animals in the 1700s. So I was pretty surprised to see that. And on a human in 1929. So catheter type stuff has been around an awful long time. It became more popular in the 40s, and then catheter-based interventions and procedures became popular in the late 70s. And late 70s, I was in grade school, and I remember I grew up in Minneapolis, a suburb of Minneapolis, where Medtronic is very, very common. And it was a career day, and a classmate brought in his dad and a bunch of pacemakers. And like Mark talked about, these pacemakers back then were probably about the footprint of your iPhone and like 4 times as thick. Today's cardiac stuff is obviously a lot smaller. So by nature, these are long, slender devices used primarily, they used to be primarily of wires and then terminations to make connections to cameras, ablation contacts. Pulse field ablation certainly become more and more common. Position sensors for mapping during procedures, temp sensors for monitoring temperatures at certain sites, and then power delivery. We're definitely seeing an increase in demand for catheter type circuits, and this is for a lot of reasons. People want smaller incisions, which lead to smaller scars, faster procedures. I know, like my father-in-law had a hip replaced a couple years back, and they had him in and out of there like same day and up and walking around. It just everything needs to be smaller and faster. Advances in technology, pulse field ablation, like I mentioned, has become more and more common. The ability to map exactly where you're at as you're looking to treat a certain segment of the heart or arteries, and then laparoscopy. I practiced that word about 10 times. I still can't get it right. And then, we're not getting any healthier as a global population. Diabetes is becoming more and more popular, kidney disease, as well as many cardiovascular disorders. And then we're getting older. The life expectancy has gone up over the last several years or last several decades and continues to rise. So we've launched a product line where we can make essentially it's a larger format circuit using very, very small features. The intent is to be able to replace a traditional wired catheter. These are built using traditional flex circuit materials. So your conductive layer is usually copper, typically pretty thin, like 9 micron or 12 micron. The reason for this is to achieve the small line widths that people want. Oftentimes you need to have a thinner copper. Polyimide is your insulator. Often these are 0.5 mil or 12.5 microns thick, and then modified epoxy adhesives to kind of laminate your different layers together. We're still making them in panels. Our typical panel width is 250 millimeters wide by as long as they need to be. Our current limitations are around 1.5 meters. And we can do up to 6 layers of circuitry. So as you need to incorporate signals and shields or multiple signal layers, we can accommodate that. These are not a round cable or a bundle of wires. They are a flex circuit in a very thin, narrow format intended to be fed into a catheter. This is just kind of an example case study. So, somebody had a part that was, a bunch of wires, a little over 1 meter long. They were having to make multiple connections. As Mark alluded to, one of the common failure points is a solder joint or a connection or a termination. By going to one flex circuit that kind of took everything from the proximal to the distal end, we got rid of known failure points, reduced assembly time at the customer's site, and then ultimately that leads to a lower total cost of ownership. This particular design is a 3-layer flex. So there's a quarter there for reference on both images. And as you can see, the one end there is very, very small. where you're just catching the edge of the quarter. This particular one had 50 micron traces and spaces and was 1.25 meters long. And then as we get into catheter capability, so this would be, as far as what we can do for you, up to a 6-layer design. Thicknesses, on the thin side for a single-sided part are going to be 0.065 millimeters for a single layer, 0.125 for a double layer, and then multi-layer is really all over the map depending on your construction and how many layers they are. So these would be using the thinner polyimide layers, thinner adhesive layers, thinner copper layers. If your needs dictate that you need to carry more current, you might need a little thicker copper, a little thicker adhesive, then your part's going to get a little thicker overall. Length, so our longest panel length right now is 1.5 meters. We need room around the border for tooling holes and processing. So our max circuit length is 1.45. Now, in certain instances, if you didn't need covers laminated on there, if it was a single layer part, we could probably go a little bit longer than this. And then overall width of the circuit, anywhere from a 0.5 millimeter to 0.8, depending whether it's a single layer or a multi-layer. And then we can add other features to these, such as shielding films top and bottom. Tatsuda is a very common one. FR4 stiffeners to rigidize certain areas in varying thicknesses, polyimide stiffeners to add thicknesses in certain areas or drive bends to a certain location. Metallic stiffeners, whether they're aluminum or stainless steel, can be bonded on either with a pressure-sensitive adhesive or a thermally set adhesive. Minimum conductor width and spacing, we're right at that 2 mil mark right now. So 50 microns. And multi-layers, we like to see a little bit more. Well, when you start talking about alignment between etched layers, that's going to depend. If it's a 2-layer circuit, we're using LDI to image these, so the registration is very, very accurate. Under 25 microns. When you start stacking up more layers, you're going to get more into that 50 micron range for alignment accuracy. And then when we look at conductors to outline, this is kind of your border requirement. We like to see more than 0.1 millimeter on a single and double-sided, and then up to 0.15 for a multi-layer circuit. The image on the left or on the right kind of shows, we can do plated through holes with these or blind or buried vias with a laser. So we have different ways we can put in the plated through holes or blind and buried vias, either with a laser down to 0.05 millimeters or mechanically drilled at 0.1 millimeters. The panel size, as I mentioned, we typically build on 250 millimeters wide and then 1.5 meters long. We can add different types of final finish. ENIG is definitely the most common and most cost effective, but we can also do electrically plated hard and soft gold in varying thicknesses as required. When we go to excise them from a panel, we can either use a laser. These are going to be for parts that are on the thinner side or narrower side, under 1 millimeter. And then if they get bigger, we can excise them with tooling. Tooling costs can definitely add to the NRE, but they could reduce the overall part cost. And then Mark had touched on impedance a little bit. So we can build in differential impedance or single-ended impedance as your needs dictate. So then kind of in conclusion, the flex circuit just adds another level of precision and reliability. When we compare it to wires, you get a more predictable flexing or motion control. They're more durable and dependable. They certainly ease and reduce assembly times, and you're eliminating connections, which we've talked about being a known failure point. We can seamlessly integrate sensors with surface mount design, putting components on. These are used for the real-time monitoring and diagnostics. Miniaturization, the flex circuits keep getting smaller and thinner and longer for that matter. I mean, right now we're limited at that 1.5 meter overall length, but we definitely envision ourselves getting longer. And then increased functionality, built to withstand your needs within a catheter application. And with that, I'm going to turn it back over to Mark, and he's going to talk about cost drivers.
Thanks, Chris. So everybody, it doesn't matter what the application is, you're always looking to try and get the most value you can for the least amount of money. And many times flex circuits are compared to rigid PCBs price-wise, even though they're not really supposed to be replacing each other. It is kind of a common thing where people who are buyers of rigid boards look at the price of PCBs or flexible circuits and wonder why they're more expensive. And the flex circuit will always be more expensive than a standard rigid PCB if you compare apples to apples, same size, shape, and layer count. It's mainly because our materials are considerably more expensive. Depending on what types of materials are required, it can be 10 times or more the cost of rigid materials. They're also very, very fragile. They're hard to handle. So typically flex circuit manufacturers don't get the same yields that a rigid board manufacturer would. And so if we have, if we're damaging stuff during processing and we have fallout, that ends up being amortized into the cost of the parts that are actually shipped out. And the materials are also dimensionally unstable. They can grow and shrink by up to 1 mil per inch just with temperature and humidity, and it's not always the same in all dimensions. So it can be a lot of fun trying to predict how the material is going to react on larger circuits. So if you look at the main cost drivers, are the same as what you would have on a rigid PCB. You have layer count, circuit size, and circuit shape and panel requirements. And these three are the heavy hitters and probably make up 80 to 90% of your total cost of your circuit. And here's an example of a processing panel. And everything that is built, unless you're buying millions of a particular part, they're going to be built in panel form. You only do reel-to-reel stuff if you are, again, buying millions of parts. So typically, these are going to be built in panel form. And ultimately, you're purchasing the processing panel. So the more parts we get on the panel, the less you'll pay per part. It's almost a straight linear function. So if we had this processing panel, and let's call this a 12 by 24 panel with a little border around the perimeter, and we put a part on it that's just slightly over the halfway mark. The best I can do when I panelize this is getting 4 parts on a panel, which means that each part is going to be 25% of that panel cost. Now, if it would be possible to shrink that by just a little bit so that you can get one part to be just slightly less than halfway, I can now get twice as many parts per panel. So reducing the part size by 3/8 of an inch could literally cut the cost of the circuit in half. So it's always important to keep in mind how you're using your panels. Fortunately for catheter users, those are typically long and straight, and they usually do panelize pretty well. But I have seen some where they'll put a right angle, like a flag on one end or the other, and that can really cause a problem with panelizing. So it's important to try and make the parts so that they panelize as well as possible. This is just another example. If you had just a square rectangular part, you can see how they panelize by adding a single arm coming off one side. You reduce it by 30%, so it's an expensive arm. In a case like that, you could probably do that connection with a single wire, and even though it's a hand operation, it might be cheaper to do that. So it is kind of a balancing act on how that goes. Another thing that can have a big impact are panel requirements. And if you as a EMS company are doing the assembly on these and you want parts shipped in panel form, it's important to discuss that with FCT before sending the panel to us for building, because we want to make the absolute best use of all of that. And so if you look at this particular layout, This is a real-time, real application where a customer wanted them shipped that way. And if you look at the amount of scrap you have on that, all that material is going in the scrap barrel, and the cost of that scrap will be amortized into the parts you ship. We recommended laying it out so that you had twice as many parts per panel. The panel size increased a little bit, but we got 3 times more parts per panel with only 50% more material used. And so that ended up dropping the cost considerably. So keep that in mind when you're specifying the actual panel layout that you want to receive these parts in. Another one we see are unreasonable X-out requirements. If you're getting a panel that's, let's say, 6 inches by 12 inches and it has 25 pieces on it, it's really not realistic to say that no X-outs are allowed, because in order to do that, there's always going to be some fallout in yield, and you'd be basically asking us to throw away 24 good parts because there's 1 bad part. So you always want to make sure that you have reasonable X-out requirements. Typically, 15 to 20% is usually a reasonable amount of X-outs to have. And almost all EMS companies can handle that, because it's pretty easy to just block out a fiducial, and your pick and place equipment will skip right over the bad parts. And so you don't end up paying a lot more for parts that are good that have to be thrown in the garbage because of an X-out requirement. And this is the layer count, and also the type of circuit, if you're going with a multi-layer versus a rigid flex. Currently, most of the catheter applications we see are single, double-sided, or multi-layer flex, so they're pure flex. I'm guessing at some point we'll be seeing rigid flex application where on one end or the other they're going to want to have rigid that's connected, and maybe some components on it. The difference is on a standard flex circuit, you can see in the upper left, all the materials are flexible. And on the lower right, you can see a rigid flex cross section, and you can see that there's hard board materials laminated to the outer surfaces. And this allows you to do SMT or through hole components on either or both sides of the application.
Hey, Mark, we had a question come in about shape. Figured we'd cover it since we're pretty close to just doing that section. Many times the shape does not depend on the PCB designer, but on the final enclosure and design controlled by the mechanical folks and end products. So many times there are no choices on the shape and length.
Well, I would dispute that. There's I've designed a lot of flex circuits, and there's always other ways that you can connect the dots. And there's also things you can do with how you maybe form a flex circuit. If you need to have a particular arm that goes off at a right angle, it's possible that you could run that up out the side and then turn it, and then in the application you'll fold that flex arm over. So there are things that can be done, and I highly recommend that you give us a call if you have an application like that, because we do have a lot of tricks on how to optimize panel layout and your circuit size and shape, and we'd love to discuss those with you.
And then there was a couple other questions related to capabilities, and we'll circle back and cover them at the end.
Okay. So getting back to the flex versus rigid flex, this is a rigid flex. You can see on the outer side there you have your SMT pads, so we can do SMT on one or both sides of this. This would be an alternative where we put a stiffener on a standard flex. And this does allow us to do surface mount on one side, and we can do through hole on the other side, as long as all of your soldering is done from just one side. And this particular design is going to be quite a bit less expensive than a rigid flex. So keep that in mind when you're doing your design. If you can keep all your components and soldering on one side, we can do just a standard flex, and that can save you some money. And functionality-wise, it's going to be exactly the same as a rigid flex. And then you get down to feature sizes. And that's where, when you start getting into smaller feature sizes, it is more difficult because of how fragile our materials are. Smaller features are going to be more fragile and more prone to not making it through all of the processes. So as your pad sizes, traces, and spaces all go down, yields go down, and that can impact it. Fortunately, most catheters are very narrow, so you don't have a lot of traces, but they are very long, so it can certainly have an impact. And here's an example. Let's say that you had an 8 mil pad and you had 4 layers that you needed to connect together. Each time you put a layer together, you're going to end up with some misregistration. And as those accumulate, somehow you have to be able to drill your through hole to make connections through all of those layers. And depending on where that hole is drilled, you may or may not be able to get the annual ring that's required. Fortunately, laser direct imaging has eliminated a lot of these problems where you can do sequential laminations and build from the inside out. This does add to the cost, but it also improves on the yields. FCT is in a good position for catheters because we're one of the few companies that has an LDI that can image over 1.5 meters in length. Most LDIs are limited to about a 2 foot by 2 foot area. So having the LDI with the extended imaging capabilities is definitely a benefit. Material types is also, we discussed this a little bit earlier. You don't want to be defining brands if at all possible. If there's a specific brand of material that you need that you think has features that others, a generic brand, would not have, we'd certainly like to discuss that with you. But in most cases, IPC certified materials are all drop-in replacements for each other, and there's very little difference between them. Certain materials like LCP and some other exotic materials, I talked earlier about the cost of materials. You could be, up to 10% or up to 10 times the cost of standard materials on a rigid board. If you're looking at things like LCP or some of the other exotic materials, those can be 20 or 30 times the cost of even standard flex materials. So before you specify exotic materials, it's good to have a discussion to make sure that you're not paying for something you're not going to get true value for. And your via types. There's multiple types of vias you can use to make the connections, through hole, blind, and buried. Keep in mind that each unique via structure has a price tag attached to it. So if you have a blind via going from layer 1 to layer 2, and you have a blind via going from layer 3 to layer 4, those are 2 unique via structures. Even though they're basically the same, they do require additional processing to do that. Buried vias are the same way. So each unique via structure has a price tag attached to it, so keep that in mind. Obviously through holes and blind vias from the outer layers in are going to be the least expensive. If we have to go with conventional laminations and you end up with buried vias, those are definitely going to be cost adders. An over-dimension drawing. I'd like to show you some that I've seen over the past, but due to confidentiality issues, we can't do that. But I've seen some things that are pretty crazy. Keep in mind that flexible circuits are flexible, and any dimension that you put on your drawing, we have to verify. And this is especially important on catheters because of the length. And so I'm going to tell you just a quick story of an example I had. It wasn't a catheter, but it was a long circuit many years ago, where a customer had a circuit that was about 30 inches overall length, and they put a plus or minus 0.010 of an inch on the overall length of the circuit. And at the time, that was missed as a requirement, and we built the circuits and we shipped the circuits. And a couple weeks later, I got a call from the customer who said, all your circuits are too long, they're out of spec. So they sent them back to me, and I measured all the circuits, and all the circuits came right in, right where they're supposed to be. So I sent them back down to the customer and said, I measured them and everything's fine. And I got a response from him about a week later. He said, I measured the circuits, they're still too long. Why did you send them back to me? And this went back and forth for about a month. And I finally figured out what was happening. I mentioned earlier that flex circuits can grow and shrink by 1 mil per inch. These were growing and shrinking in transit, and they were being shipped from Minnesota in January, where the humidity was 2%, and going down to Tampa, Florida, where the humidity was 90%, and they were literally growing and shrinking in transit each way. So the last time the guy called, I told him to take the circuits, throw them in an oven at 150 degrees for about 10 minutes and remeasure them, and they shrunk right into tolerance. So I guess the moral of that story is don't put dimensions on the drawing that really aren't necessary, and keep in mind that the materials are flexible. And because of that, only dimension things that are truly critical. If they're not critical, don't put it on the drawing. Let the Gerber files drive that. Dissimilar layer counts. This was probably not going to happen much on catheters, but it could. I've had customers in the past that have said, well, I need 4 layers in this particular area, but I only need 2 layers on each end. Can I save some money that way? And I tell them the price is going to change, but not the way you want it to go. If you've got 4 layers with any kind of interconnect in that 4-layer area, keep the same stack up throughout the entire circuit. That's going to be much more expensive than trying to remove areas that it doesn't save you any money. It actually makes our processing quite a bit more challenging. Excessive size can be a cost driver, and excessive size kind of depends on where the parts are being built and who's building them and what their equipment can handle. You'll start to see that when you get over about 28 inches, a lot of manufacturers will start to say that you're pushing their limits. In our case, we're up to about 1.5 meters, as Chris mentioned earlier. And there are a lot of customers that are looking for EV circuits for EV vehicles that are even bigger than that. So we're constantly looking at ways to increase our capabilities as far as overall size.
Hey, Mark, we got a question relating to tolerances. So considering this, what are the standard percentages in tolerances for everything you make, especially regarding vias?
For vias, the tolerances on vias, if it's a through-hole drilled via, typically what you see is plus or minus 0.03 of an inch. That takes into account the plating that you're putting into them. Blind vias are actually rarely toleranced because it really doesn't matter. If anything, I would put it a minimum on those blind vias so they don't get too small. I think the industry has found overall that once you drop under 100 microns for via size, it start to affect reliability. So we typically try to be 125 to 150 microns on our via size whenever possible. We formed down to 50 micron before, but it can impact reliability. You have to keep in mind that these are drilled with lasers that are focused, and so it's not a straight collimated beam. It's a focused beam, and so they are going to be tapered a little bit. And so whatever your hole size in the top, it's going to be smaller on your landing pad depending how deep you go. And so you want to keep that as large as possible. So, and as far as the tolerances on other things, other features, size and shape, I try to make everything reference that's not critical. Again, put only critical features, with full dimensions, make everything else reference, or just leave it off completely and let the Gerbers drive the application. Copper weights in catheters, you're typically, and Chris kind of covered this earlier, you're looking at fairly thin copper foils. We're probably looking at no more than 18 micron, and probably seeing more 12 and 9 micron foils because of the feature sizes. You just can't make 50 micron traces and spaces on 1 ounce copper. It's just not possible to do that. So as copper weights get thicker, you're going to see prices go up, and it's going to be more difficult for us to define features. Multiple final finishes. This is if you wanted, let's say, a cop or a solder on one end and enig or enapeg or some other finish on the other. That's very, very expensive because really the only way to do it is to mask one end, do one finish, strip off the masking, mask the one finish that you put on, then put the other finish on, then strip off the other finish. That's all done by hand. And anytime you start doing things on individual pieces by hand, that really drives the cost up. So it's best to pick one finish that works for you and go with that. If enig isn't, that's pretty much the standard of the industry that we're seeing. If that doesn't meet your needs because you're doing wire bonding or something, you can look at things like enapeg as an alternative, which will give you a little bit more, a few more options and isn't a huge cost driver. And so that concludes the main part of the presentation here. And at this point, we can take any questions anyone has. Just put them in the chat box, and we'd be happy to field them as they come in.
All right, we can roll through a couple of them that have come in. Do the catheter flex circuits have known biocompatibility for use up to 30 days in the bloodstream? I would say no, as far as known biocompatibility. Or do you have anything to add to that, Mark?
I had one application years ago that actually was going into an artery, and the application ended up being a failure because they were finding they were getting clotting in the blood. But after looking at it, they thought it may be the fact that they had it in a spiral pattern wound around the outside of the catheter, and they thought that that was what was causing the clotting and not the material itself. Polyimide film is pretty much inert, but I can tell you that there are several manufacturers that have pretty much stated unequivocally that their material should never be used in implantable, long-term implantable, and that may be considered long-term implantable. So you'd want to be very careful about what materials you call out if you have something that's going to be in the bloodstream. As far as the flex circuit itself, I can guarantee that the flex circuit can handle being in the bloodstream. It's not going to bother the flex at all. It's just a matter of whether there'd be some other side effect from that being in the artery or the vein.
All right, then there was a couple questions related to when you say 6 layers max, are those copper layers without counting adhesive and overlayers? Yes, those are, when we talk layers within a flex circuit, we're talking conductive layers. So that would be up to 6 layers of copper, and then, multiple layers of adhesives and polyimides to act as bonding agents and insulation.
And one thing that we, I think Chris may have covered it just briefly in one of his modules. If you need shielding on the outer layers, there are shielding materials that aren't really considered a layer, but they will give you shielding, and they're extremely thin and very, very flexible. They're less than 1 mil thick, and we're seeing a lot of use of those. So if you're looking to try and keep noise down, a shielding film versus an actual metal layer could save you both flexibility and cost. So keep that in mind.
Yeah, that essentially gets you to 8 layers, 6 conductive layers of copper and 2 shield layers, top and bottom. So
correct.
All right. When you get the time, I would like to hear about the ability to twist and flex without adding torque load.
Twisting is, I think the thing to keep in mind is that flexible circuits flex really good in one axis at a time. So twisting is typically something you have to be very careful. Now, on a catheter flex, it's very, very narrow. Twisting is not going to be nearly as big an issue as it would on a circuit that's maybe 1 inch or 2 inches wide, obviously. Almost all the load's going to be on the outer border of the flex. On a very, very narrow flex, the biggest thing is just making sure that you know what length you can have a full rotation of the twist. And as long as you can control that, it can be very reliable. So that's the biggest concern there. If you're going to try and take a flex circuit, even if it's very narrow, and twist it 3 times over 1/8 of an inch, that's not gonna survive that. So if you do that same thing over 2 inches, you'd have no problems whatsoever. And again, we can certainly help you with that. Chris and I have been doing this so long that we have a pretty good feeling for, what a flex circuit can handle and what it can't. So a quick chat would be in order there.
All right. Do you do class 3 flex capability? Question. So that's one question. Most of what we do is class 2, but we do have some class 3 product. And then the next part of it is for space application. This is for future reference. So we certainly have product in space applications, and IPC is working on space addendums. I don't know, do you have any feel for how far out those are?
Yeah, on those particular, on some of the fringe markets like that, those can take a while to develop. The space addendum, I think, has been in process for over 5 years already. And I don't know how close that is to being done. That's just a 6013 addendum, I think. Or actually, I think it's 6018. I don't know. But yeah, I don't think it's imminent. I think it's still a ways off before that's completed.
All right.
I see a question on EMI. I'll scroll up a little bit. And any questions that are asked here, if we don't cover them live here, we will get back to you and cover them individually with an email response.
Yeah. So what is the susceptibility to EMI?
Yeah, that's where your shielding film really comes in handy. It's fantastic for EMI. The only place you would have any noise getting in or out would be the edges of the circuit. As long as your 3 dielectric thickness is inboard from the edge of the circuit, virtually nothing's going to be getting in or out. So you can actually run a very, very quiet flex using those shielding films. Here's one here. It says, what's the max processing temperature for the standard materials? That varies a lot across the industry. In our case, we do have high temp lamination presses that will go up to 300C that we use if we're using it's a couple of different materials that we use that are thermoplastics that are high temp, so we can make high temp circuits. And so you're having the high temp press is something that's not common at all for most flex manufacturers. Most flex materials process under 300 Fahrenheit, so you don't really have to get those high temperatures. But because we do have the high temp lamination presses, it does allow us to go to higher temperatures.
And all the materials are created to withstand any soldering processes as well.
Here's one. How small can you go with a flex heating element? It kind of depends on how many watts of power you need in that element. I mean, we can go to the size of a pea pretty easily. I had one application where we were putting quite a few ohms of resistance in for a backup camera. So think of a camera on a car and how small that lens is, and this went around the outside of the lens. So we can make them very, very small. So it's we'd have to talk about your power requirements, your heating requirements, and the area that you want to heat, and we can tell you pretty quickly if it's something we can support.
All right, here's one. With pulse field ablation becoming the new ablation method for many procedures, are there certain design characteristics to consider for past flex circuits? So that's going to come down to how much current you're trying to carry. Certainly, we can work with you on the designs to make sure that you have proper cross-section to support the current that you're trying to carry.
Yeah, we can do a review of the design, and that's usually just a good thing to do is to keep us involved while you're in the design process. I still have military customers from a past life that will send me drawings to review just to take a look at them very quickly and flag and everything. Even though we can't do ITAR parts, I'll still review the drawings and make sure that everything is in order before they send it out for all their signatures. And ultimately, I want every flex circuit design to work, whether we build it or someone else builds it, because flex circuit failures don't do anybody in the industry any good at all. So we're trying to make things as reliable and cost effective as possible.
All right, here's one. Can you tell me about the equipment at your flex plant? So the new plant that we built in Zhuhai is truly state of the art. It has all the different processing, specifically when you talk about wet processing, like plating and developing and etching and stripping, capable of handling the very, very thin substrates and thin coppers without having to put them on carriers, so that makes that processing go better and quicker and more cost effective. You also get higher yields because we're not damaging the parts as we process them. All the different chemistries are set up on feed and bleed systems and monitored to make sure that everything is optimal. Like I mentioned, it truly is state of the art.
And Chris, there's a short video on our homepage. If you have time, grab a cup of coffee, grab a cup of tea, and take 3 to 4 minutes and look at that video. It truly gives you a good overview of the capabilities.
Then there's one just says flexibility, twist and bend.
Now we kind of talked about the twisting. As far as bending, there are guidelines in 2223, and for bending, it's 10-to-1 aspect ratio. That's circuit thickness to bend radius. That's 10-to-1 for single and double-sided circuits, and 20-to-1 for multi-layers. This is assuming 90-degree bend or less, and a static application where it's a single bend or maybe just a couple of cycles during its life, but then that's constrained in that condition. If you have a bend that's more than 90 degrees, or your bend ratio is less than that, it doesn't mean that it won't work, but you would want to have a conversation with us prior to locking in that design, because there may be some things you need help with as far as how the part is formed. I can usually tell you just by looking at it whether it's something that can be built successfully and reliably. The biggest concern is when you have a very, very sharp bend ratio. The traces that are on the outer part of that bend are going to be stretched and plastically deformed. And at that point, if the bend is exercised even a little bit, those bends, copper doesn't recompress, it ripples. And then it's like the old bending the coat hanger back and forth. You'll start to work hard in the copper and you'll get cracks on the outer layers. So it's important that if you do have a very tight bend radius, that it is constrained and you don't do any additional bending after it's formed.
All right, here's a good one. Can you talk about sensor integration, SMT, thermal layers, or Constantan? So we have a 900,000 square foot facility in Wenzhou, China, that has, again, state-of-the-art equipment. I think it's like 15 pick and place lines. So we're able to do that very accurately, very quickly. And then another way you can accomplish that is with like a thermal pile, which alternates layers of copper traces and a resistant foil trace, usually Constantan, with a via, that connection. That makes the connection between the two layers. So that's another way we can accomplish that.
All right, guys, I'm going to just jump in here. This is Katie from Global Spec. We only have about a minute left in our webinar right now. So I am going to suggest we start to wrap things up, gentlemen. So I want to say a huge thank you, Ray, Chris, and Mark. Thank you all for being here today. Thank you for a great presentation and for answering some of our attendees' questions. So gentlemen, thank you. And we appreciate your attendance today, everybody. So thank you all for taking time to attend this webinar event. Take care, and we will speak with all of you soon.
All right. Thanks, Katie.